All right, let's get kind of our act together here. As I mentioned before, this was a little different from what we were initially doing. So I'm going to go through and see where I have my VE stuff at. I think it's on this Pico. Let's see, just Pico. So on this computer screen, I got the Pico running. I went ahead and drove my Tahoe, did a VE test, and one of the things that a lot of people sometimes they get confused on is when you do a VE test, you can't just check it while it's just running. You have to drive it wide open throttle. So here's a little video of me driving my Tahoe on the way here this morning. You can see, well, I got 341,000 miles. It's just barely broken in. It's fresh. And there I go. I'm accelerating. And I go wide open throttle. Look at that acceleration. And shifts right at about 5,000 RPM. And then looks like it's climbing up to, I think I chickened out. Once it got to about 70, I didn't let it keep going. But it was about 5,000 RPM also at 72. So that's how you drive the vehicle when you want to do a VE test. You need to go through and drive it wide open throttle. And while you have your scan tool hooked up to it, and I just took a picture. I did a snapshot with my Tech 2, and I didn't have my snap-on scan tool with me, so I wasn't able to use it. But I used the Tech 2, and I did a snapshot, and then I replayed the snapshot. And what you usually want to do is you want to find the point where you've got the highest mass airflow reading. And then you take those numbers, and you look at the RPM, the mass airflow sensor reading, and you enter that into a calculator. And I have a calculator that I downloaded. There's so many calculators up there on the internet. You can use anything you want. If you just Google VE calculator, you'll find a dozen sites that have their online calculators. This is one I got many years ago, and I just kind of use it. It's an Excel spreadsheet. And so if I enter those numbers in there, you can see right here I've got roughly 202 grams of airflow per second. My engine's 5.7 liter. The RPM that was when I was getting that high MAF reading was 4828. So 4828. My altitude is not 1,000 feet, it's 400. And then basically at the bottom of this, it will give me the results of my VE calculation. And you can see right there, it says I'm at roughly 75% VE. Well, this here is a Chevy small block, and it should be pumping out a little bit better than 75% volumetric efficiency. So one of the things I did not take a picture of, but what you'd want to do at this point, you're like, okay, I'm 75% VE, volumetrically efficient, and there could be a couple things going on with the vehicle. For one, it could be 75% VE. The engine could just be pumping 75% of its displacement. That's what volumetric efficiency does. That's what it's dealing with, is that you've got this displacement engine, 350 cubic inches, that for every 2 revolutions of the engine, it should move at 100% VE, it should move 350 cubic inches of air. It does not care about fuel, does not care about ignition, it doesn't care about rich or lean or spark advance or anything like that. If you have an engine spinning at 6,000 RPM, 5,000 RPM in this case, every 2 revolutions of that engine should move 350 cubic inches of air and when I say 2 revolutions is because it's a 4-stroke cycle and it takes 2 revolutions of the engine to suck air in, compress it, power, and then push it out. So when you're done, you've got, you should be moving 350 cubic inches every 2 revolutions. That's if an engine was 100% volumetrically efficient. We're not really expecting a naturally aspirated engine to be 100% volumetrically efficient. So, usually 80% is about normal. 75 is kind of low end. And this is the thing, is some engines, like this LS engine right here, these things will do 95% VE if you test them. They're really actually pretty good. They breathe very well. And then some engines aren't nearly as good. So you end up getting a situation where you're like, okay, what's normal? If I was getting 75 on my Tahoe, I should be getting in the 80s, in my opinion. So anyway, now this is one other thing that you take a look at, which is kind of interesting. My barometric pressure on this is 100 kPa. So key on, engine off, I got 100 kPa, kilopascals absolute of air pressure. And that is equivalent to about 29.5 inches of mercury. Like if you look at a barometric gauge, and they've got, you know, the 0 to 20, I don't know how they go, but 20, usually around 30 inches at sea level is considered barometric pressure. And then when you start an engine up, you know, you got 30 inches of mercury of pressure on it, and then when you start the engine up and you pull that low pressure down, you create a vacuum in the intake manifold that takes 20 inches of vacuum away, and then you're left with, in the intake manifold, 10 inches of mercury. That's the absolute pressure. That's not gauge pressure. That's how much actual pressure you have in there. If you can pull all of that out, you know, if you've got a vacuum pump or something like that, and you can pull all the most you can pull out is your barometric pressure. So the greatest vacuum I can pull on this engine is 101 kPa. The greatest in inches of mercury, it would be like pulling all 29.5 or 30 inches of mercury out. Now, engines can't do that. They don't seal up that tight. A good running engine will usually have around idle around 20 inches of mercury, or it'll pull the vacuum from 100 kPa down to about 33, 32, maybe 35. That's the equivalent of pulling like 20 inches of vacuum. All right, I got a little sidetracked on that. But one of the things I was going to point out, notice how at wide open throttle on this, my map sensor is reading 95 kPa, whereas my barometric, it should at wide open throttle be pretty damn close to the barometric pressure. That is equivalent to about 2 inches of vacuum still in my intake manifold. Well, I should have 0 inches of vacuum at wide open throttle. I should have all the access in the world to blast, to blast air into this combustion chamber. So that might be a clue. Right there, I might have something as stupid as a restricted air filter, you know. And with 340, I don't remember last time I checked or changed the air filter, so there's a pretty good chance that it is restricted. That'd be an easy test to do. Now, before I got on this long rant about pressures and all that crap, what I was trying to get at is that there are situations where we might have a VE reporting at 75%, like in my Tahoe, the example of that, it might be saying I'm 75% efficient. Well, it also could be a lying mass airflow sensor. Maybe my mass airflow sensor is not reporting accurately. And how would I know that? Well, the reason why I might be suspecting or doing a VE test to begin with is I might have fuel trim issues. Remember, fuel trim is kind of that feedback result of the air-fuel mixture in response to what the O2 sensor is reading. So my O2 sensor looks and says, yeah, I'm a little rich, cut back on fuel, and then it's like, oh, I'm a little lean, add a little bit more fuel. Well, the computer is saying, with this amount of air coming in the engine at this speed, I should have this much fuel coming in. And then it relies on the O2 sensor to say, oh, no, you're too rich or you're too lean, and then it's going to adjust for that. And how much it adjusts, that's what we call fuel trim. And the long-term fuel trim is how far off the baseline, how far off the program that the computer had in there, and it was calibrated for based off of the engine and the speed and the amount of air coming in. The long-term fuel trim is going to adjust for things that are throwing that off. So if my mass airflow sensor was misreporting, and in reality this engine is 85% efficient, but it's only reporting 75% of the air coming in, there's air coming in there that it didn't realize, didn't report on. So I'd look at my fuel trim numbers to see if the fuel trim's saying I needed to add fuel. So if my fuel trim numbers were perfectly good, perfectly fine, and then these numbers are low, like say 60, 65, 70% VE, then I'm looking at an engine problem. If I see a low VE and my fuel trims are off, then I'm looking at a mass airflow sensor problem. I know you're thinking that might be kind of a confusing way to look at it, and it might be kind of a hard way to factor it, but think of it this way. Mass airflow sensors. We got this nice little mass airflow sensor right here on this truck, It measures the amount of air coming in. Well, the computer, knowing how much air is coming in, says, I need to inject this much fuel. And then I should have a pretty good stoichiometric mix, and the O2 sensor doesn't have to do too much, or the computer doesn't have to do too much to factor or fix that. Now let's say I got a restricted exhaust. If I got a restricted exhaust, how much air was getting into the engine now? If I can't get it out, I can't get it in, right? The restricted exhaust is going to prevent it from going out, so I got less air coming in because of the restriction in the exhaust. Well, guess what picked that up? I get less air coming in, so they mix less fuel with it. So you still have a stoichiometric mix, even though I've got less air coming in because of the restricted exhaust. If my air filter's clogged, I can't get enough air in. Well, if my mass airflow sensor is not measuring the quantity of air, it's not going to mix as much of the fuel, and it's still going to be stoichiometric. Even though it's not what I want, it's still going to be stoichiometric. So things that are wrong with the engine, the intake, or the exhaust, they don't affect your fuel trims on a mass airflow sensor vehicle because the mass airflow is affected by the things that are wrong with the engine, the exhaust, or the intake. Now, if the mass airflow sensor is wrong, and there's nothing, and it's reporting a wrong value, and there's nothing wrong with the intake or the exhaust or the camshaft or anything like that, it's expecting a different amount of air coming in than that's being reported. So they can only work off of what they know. If this mass airflow sensor is lying to it and telling it less air is coming in, it's going to mix less fuel. And then that's going to be a lean condition because you actually had more air coming in. And then the fuel trim numbers go up. Same thing if it's over-reporting the amount of air. If it thinks there's way more air coming in, it mixes a lot of fuel with it, even though there's not that much air coming in, then they have to trim that fuel out because it was too rich. So, long and short, that was kind of a long way to explain. But I do have an issue, so that'll be something I can look at. I didn't really think there was anything wrong with the truck, but I think there is, looking at those numbers. Okay, now I'm going to look at this. I took a Subaru Wrx out, nothing wrong with this vehicle. And this is kind of nice, the feature. This is Shop Stream Key. Did I say that right? Yeah, Shop Stream Key. And Snap-on's software. And give me a second here. I'm going to drag some of these values up. There's a lot of things that are recorded. And so we got engine speed. We definitely need that. And it graphs it out for us. And there's load values. There's the absolute load value and a calculated load value. And then if anything I drag up to the top will be included in this graph. So it's kind of neat. I don't know how, you might have to go full screen to be able to see it. Here's my mass airflow, grams of airflow per second. I'm just going to throw these up here where I can grab them easier. This is the command or the equivalence ratio. Equivalence ratio, since this has air fuel sensors, the equivalence ratio is basically lambda. It is my air fuel ratio. So like right here, this value it's showing is just a little over 1.0003. Well, lambda is actual over stoichiometric. So it's a ratio where you have actual over stoichiometric. So actual air fuel over stoichiometric. So stoichiometric being 14.7 to 1. So if you had a number greater than 1, you'd be lean, because like if you were 16 to 1 over 14 to 1, the number would be greater than 1. 16 is greater than 14. That's a bigger than a 1 number. Now if you had equivalence ratio less than 1, it would be a rich condition, because your actual, like 12 over 14.7, that's a number that's less than 1. So anyway, that's lambda for you. I'm going to throw that up in there. And I'm going down the list here. I did this earlier, and then my computer locked up, and I had to shut it all down. So I had it all ready to go, but you know how things are. And airflow, I was going to put throttle position in there. There's a lot of different throttle position sensors. There's throttle motor volts, throttle motor duty cycle, relative throttle position, absolute throttle position, and then here's actual throttle opening. We'll try that one. So that way you know when I'm wide open throttle. So let's see what we've got here so far. Here's my engine speed up top. I'll put mass airflow next to it. I don't even see it. Hold on. Okay. I know I dragged it up here and dropped it. There you are. when you drag these things, it doesn't scroll the list up for you. Okay, so load value, mass airflow is right there. I don't need target engine speed. What's the point of that? Calculated, I don't need crankshaft value, position sensors, cam position sensors. See if I do 6. That's kind of a good graph there, I think. I don't know. Actually, you could probably see it better like this. There we go. Now, if you look, they already have the min and max set up there. So it's kind of nice with the mass airflow sensor. Like over here, you can see the max was 255 grams of airflow per second, which is crazy to think because I got 202 on my Tahoe at 5,000 RPM, and it's a 5.7 liter engine. This is a 2 liter engine, and it got 50 more grams of airflow per second. Probably has twice as much power as my Tahoe does too. But so I look for the highest point of my mass airflow, and it's probably this one here. No, it's this one, this first one, I think. See, I'm looking at this right there. And then I can zoom in on it. See the little plus symbol in the lower right? I can zoom in, and I can see a little bit better what's going on. I can get that right onto that peak. But since it's serial data and they're spitting out pieces of information, it's not all coming in at once, it's coming out one at a time. I wouldn't be surprised if this 255 is actually related to this RPM. I'm going to call that 6,000 RPM, and then we'll say 255. So if I go back to my calculator, and so I had 255 grams of airflow per second, 2 liter, 2.0, 6,000 RPM, and enter. I got 216.24 is the actual volumetric efficiency. That's pretty impressive. That thing is packing twice its displacement, over twice its displacement. Think about that. This engine should move 2 liters of air every 2 revolutions of the engine. It's moving over 4 liters of air. Well, almost 4.3 liters of air for every 2 revolutions of the engine. That is what turbo boost will do for you. So that's pretty impressive. Now, how do you tell if that's what it needs or what the engine breathing is? It's a little bit hard because at 216. If I go back to my scanner, also notice there's this PID called a load PID, and they have a calculated load value and then what they call an actual load value. What happened to that one? It's in there somewhere. Calculated. These things are so small I can't hardly read them. Raw accelerator equivalence calculated. Oh, it's up there. Absolute load value. Look at that. It says up there in the upper right, 234. So they did their calculation, and they're saying there's 200. It's pushing 2.34 times the amount of displacement in. Now they do the kind of calculation to bring it down to what should it be, and that's where this calculated load value is. It says 100. So they've taken this into consideration that you're in the boost condition and you've got about, you're going to be packing in more. And even if there's something wrong, you're going to be probably over 100% VE, but the engine wouldn't run right. So if you didn't have the capability of seeing this calculated load value, and you can see it saying it's at 100, you can go through and take a turbocharged, supercharged engine, and you can put it in a VE calculator. What you have to do, though, is you have to go through and change the barometric pressure. You have to find a VE calculator that lets you change the barometric pressure. And then you have to put whatever your boost pressure is, or because we're going to basically lie to the VE calculator and say the barometric pressure is what this thing is getting under boost at wide open throttle. So let's see what that is on this. There is a PID. If we look at the manifold absolute pressure right here, so where are you at? There you are. Move it up to the top. It's actually 68.2. Now some of the calculators, this one actually uses inches of mercury, but if you have one that measures in kPa, you'd have to use a calculator to kind of convert that over. Now look at what it did to my VE. Now it says I'm 93.55% volumetrically efficient. So what I've done is I lied to it and told it that the atmosphere had 68.2 inches of mercury, which if it did, we'd probably be crushed into a little, I don't know, we'd probably fit in a pop can. That'd be a lot of pressure on us. But either way, we're getting, you can use, my point is you can use a VE tester on a naturally aspirated engine, on a turbocharged engine. If you have the load PID, it's worth looking at the load PID. Load PIDs are usually, not always, but usually like the computer's volumetric efficiency calculation. As long as you got a mass airflow sensor and you have a load PID, you can usually look at that. I've heard a lot of people say that the load PID should always read 100% when you drive it at wide open throttle. I don't believe that to be true. I think most engines, you're going to see anywhere between 85 and probably less than 100 at wide open throttle. This Subaru, obviously, the calculated load PID did go over 100, so yeah. But here, I can go through and check it myself, too. I can use the scan data and the PIDs and enter it in. Now, going back to that, where we were, the equivalence ratio, I think that's kind of neat to look at, because the equivalence ratio of 1.0, and my little picture's in the way there. Let me see if I can move that out of the way. I will move you. Can I? I'm clicking on it. Hold on a second. This is the vehicle tripod cam. There we go. Yeah, there. Okay. So over here in the lower right corner, you can see where it says 1.0. That's your stoichiometric. That's 14.7 to 1 over 14.7 to 1. Remember, it's actual over stoichiometric. So when you see this number change, when it went below 1.0, it's running rich. I don't know really how rich, but you'd have to do the math. In that case, I'm basically 0.7 of the stoichiometric. And then if I go, like you can see way over here, that number went way over 1, but guess what happened? That was when it got off the throttle and it went to fuel cut, so of course it went lean. So the O2 sensor saw that, and it just, that's probably where it pegs. It does, that doesn't go any higher. So that's way lean, because as soon as you take your foot off the throttle, it goes into fuel cut. So it's kind of neat with the air fuel sensors that you can not only interpret your rich or lean, but you can actually interpret how rich or how lean by looking at that equivalence ratio. All right, well, I don't know if anybody's got any questions on that. That was the little VE example that I was going to show. It shows here in the, nobody's really asking any questions on YouTube. Feed is good on Facebook. Thank you, Aaron. So that's all as far as the VE, that's all I was going to show you. If you have any questions, please post them up there. Fortunately, we try to set up something where we can go back and forth. Now, I was going to show you a few things on ignition using scopes. And I've got this little mock-up here. It's something I made for the sake of the class, and I'll show you. It's what it is I made this little shocker box. It's called a shocker box. You can buy these things, or actually you can find these instructions on the internet. On the inside, there's like a 555 timer circuit and all that stuff. And when I flick the switch on, I can change with these dials. I can change how fast it's going to operate these coils. So here's a waste spark ignition coil. Here's just a traditional. That actually came off a 99 Chevy Tahoe. Well, I don't know if it was 99, but it came off a Chevy Tahoe. And I use the ignition module over here on the side to go through and basically operate the coil. And it works pretty good. What I use it for is just demonstrate a few things as far as scopes are concerned. And that's what we'll use it for here. It's fun to create sparks and sounds, noises. You can probably see that. You probably want me to touch it, but I'm not going to do it. It's loud. I kind of wonder if this screws up with the wireless mics or video. So yeah, we're throwing spark right across that. And one of the things I like to show the students is I'm going to go ahead and show the effects of compression on this. And I'm just remembering at one time I smashed the electrode on this and created a like a no gap situation. So this, we'll have to see if it works. But I'm going to go ahead and get a secondary lead. Should have done that ahead of time. Forgot about it. So hang tight. If I had background music, I would play it for you, but I don't. I know wait a minute, I got all these leads over here. What am I thinking? Secondary lead, I'll just have to take it off the vehicle. We can do some of these tests on the vehicle, but there's really nothing wrong with this vehicle, so it's, I don't know if it would show me anything. What do we got here? Hey, Tyler Thavnot. How you doing, buddy? Still got the automotive shirt with your name embroidered on it, I hope? That's, we should buy one of those machines here so that way students can do that, because that was pretty cool. We always never forgot your name, that's for sure. Okay, so secondary leads, right? Switch back over to my other camera. So this is a typical secondary lead, and you just go around the wire, ground it out. Did that work? Okay, yeah, I don't know what, that took a while to reconnect there, but so this is the secondary lead, and I'm going to go ahead and fire up the Pico, and we'll go through and put it on a setting. Is Pico already? Yeah, it's already running actually. So channel A, my probe, I usually start, I can never remember. It's either going to be secondary inverted or secondary positive. That's where the two options come in, positive or inverted. I'll start with inverted. And then we'll put the scale at, say, let's do 20,000 volts. If you know me, I like to put a lot of time on the screen and then kind of zoom in. But actually, I won't do that this time. I'll go ahead and lower it down so we can just see one pattern. We can set a trigger up down here to repeat. And when I fire this up, there's my secondary ignition pattern. And now obviously it's just firing into the air. And I don't have it into these cylinders right here. So just bench cam. So it's just firing this plug and that plug. And I'm hooked up on on one side. I can only see that. And if I hook up to the other one, see, I don't see anything on that because it's inverted. So if you're going to check both of these, if you're going to check both of these spark plugs, you have to actually have two leads hooked up to your Pico. Now I'm going to move it over to, I'll turn it off first so that way I don't get shocked. I'm going to move it over to the one that's in a cylinder here. And let's see what it looks like then. It didn't fire up, which means that's probably the one I've got my, hold on a second, I'm going to get a wrench so I can take that out. Because I think what happens is I went ahead and crushed that electrode in there. And I'll remove the trigger so you can see what it looks like, or lower that trigger. It's a good thing about a wireless mic, I can walk halfway across the room and still talk to you guys, even though I'm not in the picture frame right now. Actually got a pretty neat little gimbal that if I had it set up, it'd follow me over there. But you don't care about that. You're here to learn about scopes. Let's see. Well, actually, I was going to show you that. I was going to show you what it looks like raw before I take this out. This is poor planning on my part. But hey, if you know me, that's pretty typical. So if I remove my trigger, you can see I'm not really getting much of anything. If I trigger it and just move the position of the trigger around to see if it'll stabilize on something. Actually, it is stabilizing on it. You can see the dwell, you can see what's trying to do on a spark line, but there's no firing line. And the reason why, and we'll see it here in a second, is because I probably have the electrode collapsed on this. If you're not firing an air gap, all you're doing is just basic. It's very easy to, there's, you know, yeah, if you take a look, this. Okay, yep, there we go. It's going to focus on that. I got the other thing in the way. No electrode. Or it has electrode, but I just jammed the ground electrode up against it. So let me move this other plug over to that side. And because what I'm trying to show you here is, yeah, we can get an ignition pattern, but a lot of people, and I always ask this question, and I asked it with the students, and some of the students went through and they asked, or they answered them, and just about all of them said, like, because I asked the question, what affects the amount of voltage, the required kV to fire a plug, the required voltage? And a lot of students said that, it was air-fuel mixture, it was air gap, you know, and those things do have minor effects. Air gap actually has a little bit more than just a minor effect, but the number one factor of kV is compression, and we're going to see that here in a second. So if I go ahead and fire this back up, move my trigger back up to a spot where it stabilizes on it, you can see right now, firing into open air, that coil's pretty much taking almost 4,000 volts. Not that much. And it is firing both plugs, but I am only measuring the one that's going into this cylinder right here. So now I've got an air hose here, and I don't know what the air pressure is hooked up at, but I'm going to go ahead and plug this in and just take a look what happens. It went over, I'm over 20,000 volts. This is the effect of just compression. So now if I take my second cursor down, it went from 3,000 volts or whatever. It went, hold on a second. I changed my scale, so let's take this off again. So you're seeing the effects of just compression on the actual amount of voltage that it takes to fire that plug from the coil. It goes from 5,000 volts to 35,000 volts. It's kind of wild, isn't it? When you look at that. If you know, there's a lot of garbage going on in that too, but we're pushing this coil pretty high, pretty hard. I don't know what its maximum output is, but 35,000 volts is pretty good for that. So let me let's go back and actually talk about what we see on a normal spark line. So we go back to 100%. Kind of zoomed in a little far there. Yeah, way too far. Sometimes it's worth looking at, you know what, I'm going to do it again, but I'm going to shift everything over a little bit. Now I'm going to zoom in on this channel to make it a little bit more, to make it stand out a little bit more. Because I had it set at that 50,000 volt scale, it kind of diminished the vertical resolution of it a little bit. So if I zoomed in 4 times, and now we can see it a little bit better. This is where the coil turns on right here. And let me switch over to just the pico. So this is where the coil turns on. And then you see this little blip right there. That's where the ignition module said, okay, we've passed enough current through this thing. We add a little bit of resistance to the circuit. We limit the current. At this point, from here to here, from this point to this point, they've already fully saturated the coil, and they realize they don't need to go through and keep pumping current through it. So they add resistance to the circuit. That doesn't diminish the magnetic field because it's still there, and they haven't turned anything off or collapsed it. So at this point, that's current limitation. And then right up to the point where the trigger is, that's when they turn the coil off. They shut it completely down, and that magnetic field collapses. When the magnetic field collapses, it induces the collapse of the magnetic field induces voltage into the coil. And there's nowhere for the spark to go initially, or the electricity to go. There's, until there's a spark, there's nowhere for current to flow because I've got an air gap. So what happens is that all that energy from that coil collapses and it builds up all this energy in there until it has a chance to ionize that gap where the spark plug is. And it takes, in this case, without any compression, it takes, 5,000 volts to ionize that plug gap. And then after it does, it's easy for current to jump that air gap. It aligns all those molecules up and just stepping stones, and it can jump across it. So it took 5,000 volts to align all that. And then afterward, it only takes, let's see, once the spark is established, it only takes about 1,000 volts to kind of keep that spark going. And the length of time that that spark is burning is what we consider our spark line length. And in this case, I'm getting 1.32 milliseconds. So there's only so much energy that we have in a coil, and that energy is going to, initially the amount of energy that we require is going to ionize that gap, and then once that spark is established, it will maintain a spark as long as it can, as long as it has energy. And at the very end there, where you see those oscillations up and down, it didn't have enough energy to maintain a spark at 1,000 volts anymore, so it just put itself out. Well, there's still a little bit of energy left. It went from 1,000 to nothing, and now it's got to sit there and wring that energy back and forth and kind of use it up. I don't know if I'm 100% accurate on this, but a lot of times you'll say when you wring this thing back and forth, you're kind of using up that voltage by oscillating it back and forth through the resistance of the coil itself. And then it's ready for the next time around. That's a typical secondary pattern. And the primary pattern would look just like this, but the only difference is that whenever we affect the secondary, the stuff that's happening in the cylinder, that stuff doesn't show through on the primary side like it does in the secondary. You'll still have a firing line. It won't be in the thousands of volts, it'll be in the hundreds of volts. You'll still see the length of your spark line, so you'll know how long the spark occurred, but you won't be able to pick up on a lot of the other stuff that's going on in the cylinder. So now, this little mock-up here doesn't always 100% transfer over to real life. On this vehicle here, if I go to hook it up, because I do have spark plug wires, these are coil overplug situations, so I can actually hook up to a spark plug wire. They got these little baby spark plug wires. And if I didn't have a spark plug wire, if I was a coil on plug, they make these wands that you can lay on the coil. Sometimes they work, sometimes they don't. The ones that are really well shielded and have igniters built into them, they don't tend to work very well on. And in those cases, some people will pull the coil out and they'll put a little jumper wire in between it to clip onto it. With this vehicle here, I cannot see, other than amperage, I cannot see the primary side of the coil. I can on the, I can check the primary. If I want, I can go through and check some of that right now. This is kind of off the cuff. I'm not really, didn't really rehearse or plan any of this. If you have any questions, post them up. I did want to point out, though, that the big contributing factor to KV is compression. One other thing that I'll mention before I forget is there's only so much energy available in a coil, right? I almost need a third hand to do this with, but maybe I can figure this out. I'm going to go back to the vehicle tripod. So let's assume that this is the amount of energy I have in a coil. Let me use the corner of this wooden piece here. If I require a lot of voltage, I should have picked something other than black. That thing, you can't even see it. Here's red, but it's shorter. It'll still work. Can you see that? I'll stick my tongue out and then that won't work. If I use most of my energy up trying to ionize the gap, I'm not going to have much of a spark line left over. So we're symbolizing this jumper wire as the amount of energy in a coil. If I spend a lot of energy trying to ionize the gap because I got worn plugs, or I got high compression or something like that, you can see I'm not going to have much left for the spark line. You need, a millisecond is actually a pretty good rule of thumb. Sometimes it'll be lower than that, like 800 microseconds. But the less energy you need to ionize the gap, the more energy is left over to kind of keep the spark line going. So kind of, if I had a finger that I could put right there, and that would actually demonstrate that or show that fairly well. So that's something that you can look at also. Okay, so if I go over and hook this thing up to this, that's cylinder number 1. I'll ground it out on something metal. It's usually a good idea. Usually the binder clips fly off and all that kind of stuff. All right, and then I thought I had an amp clamp hooked up to it already, but I got an amp clamp here, I'll take it. So here is an amp clamp. The reason why I have to use an amp clamp on this, I mean, I guess I don't have to, but the amp clamp will show the amount of current going through the coil. These are coil overplug, as I mentioned before, and they have 4 wires going to it. If I had a coil that only had 2 wires going to it, then this would have it would just basically be the primary windings, and I would have voltage going to it, and the computer would be dropping the voltage in the circuit and turning it on and off. I'm just going to pick a wire. Set it on the 20 amp scale, zero it out. Hook it up to channel B on my Pico. And we'll turn B on to the amp clamp. So if I go to my probe, 30 amp current clamp, oh no, that wasn't it. 60 amp in the 20 amp mode. And then I'll just go ahead and pick the high amperage scale. Put my cursors back to where they were. I don't know if I have this set up exactly, like it might be inverted secondary or positive secondary. Let me finish what I thought though on the igniter. If I got 4 wires going to a coil, I've got a signal coming from the computer that's probably a little 5 volt or maybe a 10 volt square wave. You know, when it goes from 0 to 5, that says turn the coil on. When it goes from 5 to 0, it says turn the coil off. That's one of the wires. The other wire is power for the coil. The other wire is ground, just a general ground. And then that 4th wire is usually some kind of a feedback or diagnostic circuit to let the computer know if something's gone wrong. That limits the amount of diagnostics that we can do. We can't get a nice primary pattern. The primary pattern would look a lot like the secondary pattern, but a lower voltage. On vehicles that have more than 2 wires going to the coil, they usually have an igniter. And on the igniter type designs, you're going to basically be able to measure current flow to it and then also see if the computer's commanding it. Now, all told, it's not hard to like swap coils and do that kind of stuff. But you always hear students or techs, they say, okay, I had a misfire in cylinder 1. And I swapped coils and it still stayed with 1. Well, I swapped injectors and it stayed with 1. Okay, you swapped plugs, swapped everything. But did you ever check to make sure that you had a good ground for the coil? Or did you ever check to make sure that the coil was actually being triggered through the wires? So swapping parts, sometimes people will swap all these parts, the problem stays with it, then they automatically assume they got something mechanical going around with it, but realize that there's a computer and wiring and connections that are supposed to be controlling those devices, and you don't want to forget to check those. And that's where the scope comes into play, and there's other ways to do it, obviously, but I'm going to go ahead and start this up. We'll see if we've got these things hooked up properly or correct. Well, I can see my amperage. Yeah, it's already. I got lucky, both situations. I can see my amperage. And I can see my voltage. It's a beautiful thing. Now I'm going to go ahead and switch this kV scale or unzoom it. I remember I was zoomed in 4 times. So I'm going to go back to 1 time. 1.0. I might shrink my amperage down. You can see I'm drawing about 8 amps. And if you actually line this up, you can see, or let me go back and zoom up on it again. I jumped to conclusions too quick there. You can see the effect on the secondary when this current turns on, when the coil turns on, and the second they turn it off and amperage goes to 0, that's when we get our kick. Now I'm going to show you guys something here because this is kind of fun to do. I'm going to crank my time base up to, let's say 200 milliseconds per division. And I'm going to turn my trigger off. So right now this thing is running, idling. And it takes about 3,500 volts to fire that plug. Now I'm going to crank it over wide open throttle, clear flood, with compression basically giving us our effect there, and we'll see what kind of effect compression has. Let me make sure my sampling's up high. Yeah, it is. See over here on the side where it's a sample interval, 260 nanoseconds. If you're checking the voltage, you want to make sure you're at least 1 microsecond per sample or faster. And here I'm a 1/4 microsecond per sample, so that's beneficial. And you can see all that on the properties side. So I'm going to shut it off and do a wide open throttle, clear flood crank. So I'm key on, engine off. I go wide open throttle. I got a couple kicks there, but the problem that I had is for some reason it was killing the ignition. Let me try it again. A lot of times it will just kill fuel, but it looked like it was trying to kill ignition on me there too. But all right, if I stop it, did I stop it in time? I only had 6 screens recording there. Oh, good, I got one. But look at there, the KV cranking, 14,000. So at idle, the running compression is probably 60, 70 PSI. And then at cranking, my cranking compression is probably 180. And you can see my cranking compression required almost 15,000 volts, and my running compression only required 3,500 volts. So hey, you know, compression makes a big factor on how much kV it takes to fire a plug. Wonder if you knew that. Now you do. Okay. So, I'm going to see if there's any other questions. I don't know. The thing wasn't automatically scrolling. I guess I should have checked. Pulling up the late nights. Hey, Matt, I miss you, buddy. Need to go through and remember we were going to make our own series, Auto Shop. Kind of like Scrubs, though. Yeah. Still want to do that. Wow, I'm about to go to sleep. Now I'm interested. Hey, I'll woo you to sleep, guys. I'll woo you to sleep. Yeah, the old superimpose and raster patterns. It's a little harder to do that with these scopes. Why is cranking compression higher? And I showed that with this other mock-up. If you tuned in a little late, here's the bench cam. This little mock-up here has basically spark plugs going into a cylinder. It looks like a little pipe bomb. Looks like something that you wouldn't want to take to an airport. But when you pressurize it, okay, and I know what you're asking. You're saying, why does it do that? And honestly, I don't really know why. It's must be harder to ionize the gap when you've got high pressure in there. And some guru probably knows better than I do, but man, I don't really know the true answer. All I know is that that's what happens. And it does definitely go up quite a bit. When I was doing it on this example here with this mock-up, it took quite a bit. It went, I can't remember now, but it was like 5,000 volts to fire it in open air, and then with pressure on it, it was 35,000 volts. So, and that was shot, just, you know, compressed air. No, nothing fancy, no fuels or anything like that. I could tell you a story. I made these little pipes like this because I was checking out an O2 sensor one time. This was fun. And I put 2 heated O2 sensors in there. And this is the thing. Most people that think of how an O2 sensor works, they'll describe it like this. The O2 sensor compares the amount of oxygen in the exhaust to the amount of oxygen in the air. And if there's a great difference, it creates a high voltage. And if there's a small or a low difference or a slight difference, it doesn't create that much of a voltage. I'm like, okay, well, that's actually false. And, you know, I hate to say that, but honestly, you could believe it like that and it still works perfectly fine. Because oxygen by itself doesn't do anything. You need to have a fuel in there. You need to have a hydrocarbon, some hydrogen. Right? You don't have to have hydrocarbon, but you have to have hydrogen. Oxygen sensors are like basic tiny little fuel cells. And I read this on the IETN 15, 20 years ago, and I was like, BS. I don't believe it. So I decided I was going to make my own little contraptions around the same time I made this. I took this pipe and I welded an end on it, and I actually left the other end open. I was going to close it off mostly and just leave a small hole, but on the end of the pipe I had these bungs where I could put gas in there. So at first I filled it up with nitrogen, just pure nitrogen. And I figured, okay, with the heated O2 sensors, I had 2 of them in that were different part numbers, so that way I could just kind of check to make sure that I didn't have just something weird going on. I was just checking the output voltage of it with them heated. And I pumped nitrogen in on one side. And using the theory of comparing oxygen on the outside and oxygen on the inside, and if there's a great difference, you should get a voltage, I should have gotten a volt, you know, as much as I could out of it. But I got nothing. It was like millivolts, like 20 millivolts or something. Then I mixed argon in there. So I had just argon in the tank, in the tube. O2 sensors were still putting out like 20, 30 millivolts. Then I put oxygen in there. Didn't change it, which just what doesn't surprise me at all, because with oxygen in there, you'd expect it to be low anyway. So then I took a little bit of propane and blipped a little bit of propane in there and shot up. So it was with nitrogen or argon and propane, it shot up. So it needed the hydrogen from the hydrocarbon to complete the chemical reaction on the tip of the O2 sensor, and that allowed oxygen to pump through the ions, the zirconia of the sensor, and combine with the H, the O2 pumped through, and combine with the H from the propane or the acetylene or whatever I was pumping in there, and then boom, and outputted a voltage. So I thought that was kind of interesting. And this is where I got in trouble. So I had acetylene pumping in there and nitrogen. And I was like, okay, I was getting a volt. I was like, wow, okay. And then I'm like, I wonder if I bled in some oxygen. If I could bleed in a little bit of oxygen, can I get this O2 sensor to kind of float around stoichiometric? So I'm bleeding in some oxygen, and then boom! The heated O2 sensor will ignite with enough oxygen, will ignite the acetylene in there, and it shot a flame out of that thing 10 feet long and about made me pee my pants. So anyway, these little pipe bombs that I got welded up over here, they kind of made me think of that. But anyway, yeah, I made those just for demonstration purposes. And I almost died that day, but I didn't. I was living well, as you can see right here. Late nights at the tech, but okay, so yeah, ignition. You can check the amperage. We did go through and kind of look at that. If I go back to my little Pico screenshot there and I zoom in it, the amperage isn't going to change really. Every time this thing runs and it cycles, it's gonna the amperage is going to pretty much look the same. Now, if you have a shorted coil, the shorted coil will show a vertical hump right here. It'll kind of be like, as soon as it turns on, it'll be a vertical hump, and then the computer adds, or the module will add current limitation to it, and then you'll see it taper off. You'd almost think a shorted coil would show way more current because it's shorted, but in reality, sometimes they actually show less because they add the current limitation to it so quick because they detect that it's shorted. So the telltale sign of a shorted coil is to look at the very beginning of the amperage ramp, and if it jumps up vertically, that's no good. That's a bad coil. Now, if I added a third channel, I could pretty easily. The only thing I would see on this Sierra right here is that I can look at the command from the ECU or the PCM turning the coil on and off. And what I would do is I get a square wave. So the coil would come here, turn on, 5 volts. That tells it the module inside the coil to turn on. And then when it goes from 5 to 0, it tells the module to turn off, and it throws a spark. So, all right, now, something else to think of. Kind of if I were to go back, if you kind of anticipate or guess what would happen, we could try this real quick. This will probably be the last thing we test. What would happen if I took my secondary clip, put it on this plug wire on this mock-up. There's another thing I could test here that you guys might get a kick out of, because these vehicles are test vehicles. I don't know if I have access to it. I could drill a hole in the intake manifold just before the cylinder head and create a leak, a vacuum leak just on that cylinder. It's a plastic intake manifold. It'd be pretty easy to do. But Mr. Crump said that I'm a mad scientist. Come on now, just because I got crazy white hair doesn't make me a mad scientist. But anyway, what I was going to show you that I brought from home, because everybody's got these hanging out at home, is I got a 100,000 ohm resistor. How do you think this secondary pattern would look if I added 100,000 ohms of resistance to it? So if I started my scope back up, I'm going to drop it back down to, you know, a triggered signal here. Repeat. And start it. Oh, I took my wires off. Just gonna try not to get shocked. Usually happens, but. So, right, you know, we're seeing here on my mock-up. You're not seeing anything, are you? That we're getting about 4,500 volts. If I go ahead and I cut that spark plug wire, see if I can find a pair of side cutters, and maybe try to jab this resistor in there. I don't know, you guys get 911 on speed dial in case this thing puts me out. I'll do it up here so that way I can rest it above the oh shoot, this might be, maybe I should have tried this before I went live. Well, I don't know. I'm going to cut this short because I don't want too much metal hanging out, or else it'll probably jump somewhere. Probably me. Let's see if I can find a pick real quick where I can jab it in there and open it up a little bit. Probably do what I usually do with a pick and jab it through my finger. I got bad luck like that. On Wednesday, I'm going to do something similar with my NVH class. We're going to look at a few things on stability control, and it'll be late night again. I surveyed the students to find out when they are available, and just about everybody picked the 9 to 10 o'clock time frame. And Matt, you are East Coast time, aren't you, buddy? So, then again, didn't you also work weird hours? Cummins, I assume you're still there. More resistance, more amperage. Don't jump the gap. The interesting thing, we'll see if this holds true, is that usually the required voltage does not change. It just moves the spark line up. So where the spark line and the firing line intersect will probably be a little higher than it was, because we still have continuity. Hell, for all I know, this won't even work. Might have to edit this all out later, you know what I mean? Yeah, because the audio would also go through this. All right, now we're good. Jeez. There's always a battery issue going on. Yeah, all right, so we're back. Hopefully I didn't lose you guys. Probably tuned out, said screw this crap. I got better things to do. Oh, I see sparks shooting around that thing. That's, maybe 100,000 ohms is too much. Yeah, it ain't working because it's jumping over the ceramic. So I don't think my little test is gonna work. I'd have to somehow try to put some insulation around the ceramic, because if you saw what was going on here, bench cam. You can see us jump around it. We can see what that pattern would look like anyway. Actually, it did raise the kV. But it's not very, it's not a good test. That test failed miserably. All right, well, I'm going to go through and scroll through 1 minute. I don't have any audio right now. Crumb? No? Can you hear me? I should have. I see it peaking up here on my thing. I know my video died out a second ago, but I changed the battery, so I should be good on that. Let's see what they have. I think a few batteries died. Yes, Grace, I changed that out. So hopefully you didn't tune out, but I'm pretty much done. Okay, you're in Indy. Okay. All right, well, if you tuned in late, what I did is I covered earlier using a volumetric efficiency test, using a VE calculator. I used my Tahoe as an example, and it had about 75% VE, a little low. And if you went back and watched that, if you didn't see it already, one of the things that was noticeable is that even at wide open throttle, I was still pulling a couple inches of vacuum in the intake, so maybe I got a restricted intake or restricted air filter or something like that. And time to put that can in cold air and that cold air intake on there, huh? Got to squeeze a couple extra ponies out of her. But then I also did it on a turbocharged Wrx, and it's a little different doing a VE test on something that's turbocharged, because you have to take into consideration the fact that it's boosted. You're not just putting atmospheric pressure in there, you're squeezing more air in there. And it was kind of interesting on that to see that it pushed 255 grams of airflow per second through that engine, which is 50 grams of airflow per second more than the Tahoe, yet that's a 2 liter compared to a 5.7 liter. So it shows you that pretty much everything should have a turbo or a supercharger. That's basically a new thing now that I believe. And you doing the VE test on something like that, you can do one of two things. One is you could just not do a calculation, look to see if there's a PID on the scan tool for calculated load, and let it the computer do the math for you. But I kind of recommend still using a VE calculator, because you don't want to trust what the computer's calculating. You want to look for it yourself. And what you have to do is, instead of putting barometric pressure at the real barometric pressure, you put the maximum boost pressure that you got when, where you're taking your readings, the RPM, the mass airflow, look to see what your absolute manifold pressure is, and enter that into the calculator. And basically you're treating it as if the barometric pressure is what your boost is. And that way you can see if that would actually equate to a proper airflow. And in that example, we got about 95% volumetric efficiency through that Subaru Wrx, which would be perfectly good, and there's absolutely nothing wrong with that engine, so I expect that to be fine. But it's good, it shows it actually kind of making sense. So, and then I wanted to show some of the ignition. I'm just kind of summarizing what we did here. You could see that compression is a major factor in KV, and spark line shows you the condition of the spark on the secondary side. Spark line length on the primary side shows you that you actually did get a spark, and it shows you how long it is, but a lot of times you won't be able to see all the fuzzies and all that kind of stuff going on. I did not go through and cover what would happen in this situation, like with a rich or a lean carbon filed or anything like that. I don't have any of those examples to show you. You can usually see that in the spark line. It takes a real keen eye to be able to look at a secondary ignition and say, yes, that one is a little lean, that one's a little rich. Typically with a spark line, the first third of a spark line, you usually see it slope down a little bit. And then the second 2/3, you usually see it curl up, because it's, as that heat grows inside that spark, it will usually cause an increase in kV to maintain that spark line. So maybe if I can get some examples of that, I'll do an add-on to this at some other time. But anyway, I don't see any questions, anything that anybody's specifically asking, so I'll probably... Turbos for base models, new standard, yes. So, sorry about the little audio issue and the fact that my computer puked out on me, or the battery puked out on me. Thanks, Jeff. Says, as the best teacher, thanks for classes. No problem, I'm here for you. And on YouTube, nobody's commented in a while, so. All right, and there's only 3 people watching, but you guys, there's 12. So anyway, I'm gonna go ahead and cut it out now. And like I said, on Wednesday, I'm gonna do something a little bit on the stability control, probably gonna look at this truck, look at a yaw sensor, go through some of they've got, there are special functions that they have with the scan tool, kind of point some of those things out. It's nothing too crazy or complicated, but they do have a pretty neat little process. It's kind of confusing the way the wording is, but if you have a wheel up in the air and you go through the process, it will activate these solenoids, and you can go out and check to see if the solenoids are doing their job. If they're holding pressure at a wheel, if you're applying pressure at the wheel, it should rotate when it should, and it shouldn't rotate in different circumstances, and we'll go through and demonstrate that. And then also go look at the yaw. It's like a Texas sensor we got over there, a yaw sensor, and a lateral and a longitudinal accelerometers, and you know, just simple stuff like that. In this NVH class I'm teaching online right now, this is where we're going through is the stability control, and then the next phases will be noise, vibration, harshness, and all that, 4-wheel drive, all that kind of stuff, and I'll probably be doing something similar for those topics as well. But so tune in on Wednesday if you're interested in that. And other than that, thanks for attending or listening to